Guys ready to go? Let's do this thing. So guys, topic of the day. Balancing chemical equations. You did? Nice. You have a frame of reference, unlike the rest of us. So guys, the date today is the 6th. Again, the topic is there. But you've already got that in front of you because all of the notes that you need to take will fit conveniently in that half blank page space that I gave you at the top of this page. So guys, we are going to today learn a skill. This is not a concept, this is a skill. It's a thing that you've got to be able to do. So when you see this on the study guide, it ain't going to be under the no's, it's going to be under the do's. But guys, in order for you to understand how to do what we're going to do, what we need to do is give this some sort of context so that you understand what we're doing. So, guys, it goes like this. Think back to the last lab that we did. Can you picture it? It's the only lab that we've done in a crucible. Can you picture it? What was in the bottom of the crucible after you cleaned it? Little strips of magnesium. Please don't write this down. But guys, what you saw in the bottom of that crucible were little strips of magnesium that we write like this. Then guys, what did we do to that magnesium as we heated it in the bottom of the crucible? We reacted it with oxygen. So guys, what happened is the oxygen that was in the air surrounding the magnesium reacted with the magnesium, and we ended up with a product. And then guys, whether you got this right relative to the empirical formula or not, magnesium is +2, oxygen is -2, and so the product that was in the bottom of your crucible was magnesium oxide. Guys, what we've just done is written what's called a chemical formula. So guys, chemical formulas are sentences that represent chemical reactions. Here's the problem. They're not that simple. So this is actually not the chemical formula, the chemical equation for what happened inside of your crucible. Here are the things that are different. Guys, it turns out, and we're going to talk more about this later, this is our goal for today. Guys, oxygen is freakishly reactive. Oxygen, when it's by itself, cannot stand to be by itself. It's like a really, really clingy person that, you know these people, right? That they can't, like if they're in the hallway by themselves for more than 10 seconds, they just fall apart. They need to be attached to somebody, right? So guys, oxygen is the same way. If oxygen is not bonded to something else, it will bond to another oxygen. So when we see oxygen on its own, it's not truly on its own, and we represent it as O2. But now, guys, we've got a problem. How many oxygens are going into this reaction? 2. How many are coming out? Why is that bad? You learned a law that would say that that's bad. Law of conservation of mass, which says what? Matter is never created or destroyed. And you see, guys, we can't just destroy matter. We've got to have everything that goes in has got to come out. So as a result, we got to start playing with this. And here's how this goes. So we go, okay, if we've got 2 oxygens there, we've got to have 2 oxygens here. But we can't do that. Why can't we do that? Because now the charges don't balance. Magnesium is +1, magnesium is +2. I can't even write. Good heavens. Let me try this again. So guys, magnesium is +2 and oxygen is -2, and that means this formula can't exist because now we've got a total negative charge of -4 and that doesn't balance. So we need to figure out a way to get 2 oxygens without changing the chemical formula. And here's what we do. We put a 2 in front. Now how many oxygens do we have? We got 2 because we've got 2 of the entire compound. But now do you see the problem? Not only do we have 2 oxygens, what do we also now have 2 of? 2 magnesiums, and now we've got to go over here, and now this thing is finally balanced. You're going, holy stinking, you got to be kidding me, right? Guys, this is what you're going to learn to do today. That entire process that I stepped you through, first in red and then in blue, is the process of writing balanced chemical formulas. So understand, the stuff that I just showed you, we're going to spend the rest of the day learning how to do well. You get the idea? Okay, so guys, in order to do this, we are in fact going to define some terms, and then we're going to talk about steps, and then this is going to become wildly practical because we're going to get to work. So guys, it goes, you're good, Mason. So guys, it goes like this. Let's write down these definitions in your notes. Thanks, buddy. So guys, let's define this. If we're going to talk about balancing chemical equations, we should know what one is. And we've already talked about this, but let's put it in writing, so to speak. So guys, a chemical equation is simply a thing that is used to represent a chemical reaction, like the magnesium and oxygen that are bonding together in the bottom of your crucible. Now guys, when we properly write chemical equations, what you're going to find out is this. They have to have three parts. Every properly written chemical equation will have three parts. You've got a left-hand side that we call the reactant side. Just like in English we read from right to left, in chemistry we progress. It's a Monday for being a Tuesday, right? Guys, just like in English we read from left to right, in chemistry we progress from left to right. So on the left is the stuff we start with, the reactants. Then guys, we've got an arrow in between. The arrow literally denotes movement. We're going from reactants to then the things that are produced, which we call products. Now guys, understand that arrow is read as yields. So together we would say reactants yield products. And guys, the arrow always points at the products. The products don't necessarily have to be on the right, but the arrow will always point at the products. And 99% of the time the products will be on the right. Mason, what did you give me? Oh, got it. Oh, that's right. You realize the important implication of this, right? Stop snowboarding. When my kids were born, seriously, they were in the car carrier when we very first brought them home, and I looked both of my children in the eye and said, "Son, daughter, I love you, and you will never snowboard." And that was it. That's how we started light. No, actually I did say that, but, and you got to understand, Mason had a snowboard injury, an accident and an injury. I hope you don't mind me telling people, because I just did. I frankly wish I could snowboard. My body's just incapable of it. I can't wrap my head around it, but there you go. All right, guys, you all caught up? Okay, so here's what we now know. Reactants typically on the left, products traditionally on the right. The arrow in between we read as yields. And guys, the products don't have to be on the left, or I'm sorry, the products don't have to be on the right. The reactants don't have to be on the left. The thing we can always bank on is the arrow will always point at products. You good? Okay, so now that we've talked about sort of the fundamentals, guys, this is going to be important for us throughout the remainder of the year. We've got to talk about something called diatomic molecules. So remember what we said about oxygen. Oxygen is so freakishly reactive that if there's nothing else to bond to, it's going to bond to another oxygen. Well, guys, it turns out oxygen is not the only substance, the only atom that does this. But when they do, doesn't this make sense? What does di mean? Two. Diatoms, two atom molecules. Guys, oxygen, when it bonds to another oxygen, forms what we call a diatomic molecule. So it's literally a molecule that is made of two of the same atoms. And you know that oxygen does that, but oxygen's not the only one that does. So diatomic molecules are molecules composed of two of the same atom. But guys, again, oxygen's not the only one that does this. I got to go over here and get in laser position. So guys, oxygen's not the only one that does this, but you need to know the 7 that do. Now, you could memorize these, or you could figure out the pattern. So guys, this is the, well, let me show you the pattern, and then when you write them down, or maybe you won't even need to write them down. So guys, this is the pattern. These are the 7 atoms that bond to themselves if they got nothing else to bond to. Start at iodine and go up until you can't anymore. Then go left, there's oxygen, right? Go left until you run out of red, and then bunny hop over to hydrogen. So it goes iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. Those are the, and the only 7, but those are the 7 elements that will never be by themselves. They'll either be bonded to something else, or they'll be bonded to one another. So if you want to write them down, here they are. It's I2, Br2, Cl2, F2, O2, N2H2. But guys, perhaps you don't need to write them down because you realize if you can just find iodine and then go up, over, and hop, you'll never lose track of these. The thing that you are going to lose track of is you're going to forget that these are diatomics, and it's going to screw up the entire balancing of your equations. But guys, keep in mind, these are the diatomics. And again, the important so what is that they'll never be by themselves. You guys good on that one? Got it all written down? Okay, so guys, you are now about to see your last page of notes. Can I get rid of this? Okay, this is it. So, and you're not going to write all of this down. But guys, what we're going to do now is I'm going to give you the steps for writing balanced equations. And then guys, we are going to do one very visually. Then we're going to balance the ones that I've given you in your notes. And then you're going to have time to work on your homework. You guys ready to jump into this? So guys, be very careful about the notes that you're taking here. For example, I would suggest to you this. Here's the question. Why do we have to balance equations? Because everything that goes in has got to come out. Says who? Why does everything that goes in have to come out? Law of conservation of mass, which you already know, right? So writing this down would be unnecessary, but it is worth reminding ourselves that if matter is never created or destroyed, everything that goes in has got to come out. So the number of reactant atoms has got to equal the number of product atoms, and if that's not the case, we violated the law of conservation of mass. And guys, that's what balancing equations is all about, is making everything that goes in come out. Okay, so guys, here's the way we're going to do this, and again, don't write this down. Here's how the next couple days are going to unfurl. So guys, and actually, you know what? Maybe this you should write down, but it's just going to go down to, well, you're going to be about here. Can you make that fit in the space you have remaining in your notes? If it turns out you can't, you can always bleed onto the back. But guys, these then are the steps that you need to write down for balancing equations. So step number 1 is this. When you're balancing equations, and again, we're going to treat these as steps, number 1, number 2, number 3. You'll notice they're not numbered though, and I'll show you why in a minute. Guys, when you're balancing equations, the first thing you need to do is identify your reactants and products. Makes sense. If you're going to balance it, you need to know what's coming in and coming out. Now guys, what you're going to see as you're following along with me is that some of the stuff that's going to come up on the screen is in blue. Don't write the blue stuff down. So, step number 1, identify your reactants and products. Now guys, here's the deal. You're not going to do that until next time. We're going to talk about how to do that on Thursday. That's why I didn't number these steps, because we are not always going to start with step number 1. Today, I'm going to give you the reactants and products. On Thursday, that won't be the case, but there's more you need to learn. So step 1, when necessary, is identify reactants and products. Step number 2, write the chemical formulas for the reactants and products. This we're going to do in about 15 minutes. So guys, to do this, you balance the charges, but you don't try to balance the equation. And that'll make more sense when we do this, but we're not going to do this for a few minutes. Then guys, there's only one more step. Then I'm going to give you my 5 tried and true tricks for making these easier. You can sell these to your friends in college if you'd like. So guys, step number 3 is this. Then you're going to balance the equation using coefficients. This we're going to do right now. So we're going to do these backwards. We're going to start on step 3, which is just balance the equation using coefficients. Then once we feel comfortable with that, we're going to go up a step, and we're going to write the formulas for the reactants and the products. And then guys, starting on Thursday, you will be identifying the reactants and products. But we're going to start low, so to speak, today. Now guys, as we do this, here's what you're going to find. You're going to get into these, and sometimes these just flow. They're super easy. Sometimes, frankly, they get frustrating. And when they get frustrating, you are going to be thankful for my helpful hints. So guys, I'm just going to give them to you. Tuck them away in the back of your brain, and you'll see that these will dig you out of trouble spots when they occur. So guys, helpful hint number 1 is this. I don't expect this to make any sense to you. Just write it down. When you are balancing equations, if you can balance the polyatomics intact, what does that mean? You'll see. But guys, trust me, you're going to be really thankful when you can balance polyatomics. It makes your life a lot easier. Helpful hint number 2, if you get an odd-even conflict, what's that? You'll see. If you get an odd-even conflict, what you're going to do is you're going to take the source of the odd number and you're going to double it. The math gods have allowed that if you have an odd number and you want to make it an even number, all you have to do is multiply it by 2, and that always makes your odd number even. So if you have what we call an odd-even conflict, you're going to find the source of the odd number, double it, and then it magically becomes an even number, and then things tend to balance more easily. Helpful hint number 3, balance oxygens last. Guys, you're going to see that there is oxygen spread all out through this thing. Never try to balance the oxygens anytime other than last. You're just digging a pit for yourself. Guys, following that, hint number 4, when all else fails, trial and error. Put a 1 in front of the very first substance. See if you can get it to balance. If you can't, erase everything. Put a 2. That doesn't work, erase everything. Put a 3. Eventually, you're going to get this to balance. But guys, obviously, step number 4, and frankly, a lot of these other steps, all comes back to step number 5. Use a pencil. I pray you don't write that down. Guys, do these in pencil. You are going to be erasing a lot. So if you're trying to do these in pen, you may as well not even try, because you're going to create such a mess, you're not going to know up from down anyway, and you're just going to get in trouble. So, look, stolen ACT pencils. Who needs one? These are pretty sharp. I'd better not throw it. That would be a sad way. Wait, you have one.
This is yours.
What just happened? Good night. Who needs... Wait, you have one. Am I the only one that's confused? All right. All right, you guys good? You good? You caught up? Did it all fit in the note space? All right, so guys, here we go. Do not write this down. Here's what we're going to do. I am now going to step you through this three-step process. Identify your reactants and products, write their formulas, balance the equation. But guys, I'm going to do this in a visual way, hoping that that can not only connect you with the process, it can also connect you with why we do it, the way we do it, and also help you understand this idea of the law of conservation of mass informing what we do. So guys, this is what we're going to do. We are going to balance this equation. Now, of course, you guys are all wildly familiar with this equation. So guys, what do equations do? They represent reactions. So when I say that you're familiar with this equation, what I'm actually saying is that you're familiar with this reaction. And guys, I know that you are all familiar with this reaction because I would be willing to bet that every single one of you has done this chemical reaction. So what does this represent? Well, guys, let's talk. What's this? Oxygen. Where do we find oxygen? In the air, other places as well, but in this form we find it in the air. And why is that 2 there? It's diatomic. Why is oxygen diatomic? Because it's so reactive it'll bond to itself if there's nothing else around. Is oxygen the only one that does this? No, there are 7 of them. They start at iodine, go up, over, and hop, right? You good on that idea? Okay, so guys, how about that? Water. We're familiar with water. I'm suspecting you're probably good with this guy too. Carbon dioxide. So guys, look at what we've got. We've got oxygen. Is that a reactant or a product? It's a reactant. How do we know? Because the arrow points at the products. So guys, this is a reactant and oxygen's going in. What's coming out? Carbon dioxide and water. Okay, and I love that you're seeing this. How many oxygens are coming out? 3. Going in, 2. This isn't balanced. But guys, right now what we're trying to do is identify our reactants and products. So here's what we know just from our vague understanding of chemistry. We know that oxygen is going in as a reactant. We know that carbon dioxide and water are coming out as products. But guys, previously I presented to you the idea that all of you have done this reaction. So in order to figure out what this reaction is all about, we need to know what this is. I'll tell you this. This stuff, C3H8, comes in big water containers about this big around and that tall. It's propane. Guys, this is propane. C3H8 is propane. And every time you light your barbecue grill, assuming that it doesn't burn charcoal, guys, every time you light your barbecue grill, this is the reaction that takes place inside your grill. The propane from the tank mixes with the oxygen in the air. It also releases a lot of heat, and we're going to talk more about that later. But guys, that's not the only thing that comes out. When you light your barbecue grill, what is coming out of your grill other than tasty burgers? Look at the products. What else is coming out of your barbecue grill? Carbon dioxide and water. Now guys, where does the carbon dioxide go? Into the air. Where does the water go? Also into the air. Guys, the water is not released as a liquid. When that water is formed, it immediately boils, turns into steam, and comes out the side of your grill along with the carbon dioxide. So now guys, you're thinking, great, water comes out of my grill. Well, guys, at the end of this unit, we're going to be able to do this calculation, but I'll just tell you the results right now. Guys, if you burn your barbecue grill for half an hour, you release about a cup of water. Here's the thing that's crazy. I don't know if you know about this. Guys, anytime you burn a fossil fuel, one of the products is water. Propane is a fossil fuel. One of the products is water. But so is gasoline. Did you guys know that? That when you burn gasoline, that water vapor comes out of your tailpipe. Have you ever seen that on a really cold day? And it looks like there's like smoke coming out of the tailpipe of the car in front of you at the stop sign, right? That's not smoke. What is it? It's actually a cloud. It's condensed steam. Out of the tailpipe of your car, you are actually releasing a lot of water. And when that water hits the cold air, it condenses into a cloud. That's literally what you're seeing come out of the tailpipe. It's not smoke. It's actually steam. Now, here's the thing that's crazy. I don't know if you know this. Did you know our military has figured out a way to collect this water and provide it to soldiers to drink? Yeah. So where are our soldiers right now? Where are we, boots on the ground, fighting? In the desert, right? And there's not a lot of water in the desert. So guys, our government actually outfits Humvees and other military vehicles with condensers. What they do is they actually place a chilled coil in the exhaust of whatever that vehicle is, and as that water vapor in the exhaust, right, this is coming right out of the engine, as that water vapor crosses across that chilled coil, just like when this steam hits the cold air here in Utah, guys, as this water vapor in the exhaust hits this coil, it condenses and turns into droplets. And they pass those droplets through a carbon filter to get out any of the pollutants. And it collects inside of a big, like 5-gallon jug that's mounted up underneath the Humvee. And guys, that can be water for our soldiers to drink. And over the course of them out driving hundreds of miles in the desert, they actually produce gallons of water. And they collect it and use it to drink. You guys not know this? They don't teach you anything in this place, do they? All right. So, anyway. So, do we have... No, we're running out of time. I was going to tell you another story about... Have you guys... Never mind. Have any of you ever worked construction? Have you ever worked in a house that's being built? And what they do is eventually the house is close enough to being done that they want all the subcontractors to get in there and get things done, but they don't have like the heating and air conditioning system in. So they close up all the windows and they put those huge propane furnaces in there, and they just fill the house with heat with these big just propane blast furnaces. You know that the painters can't come in and paint on those days? The painters can't come in and paint the house until the actual furnace is in there. Because if they're heating the house with these big propane blast torches, the painters can't paint. How come? Fills the house with water and the paint won't dry. Huh? Guys, all right. So, guys, here's the... You're learning so much. All right. So, guys, here's what we got. We got propane and oxygen going in. We got carbon and dioxide and water coming out. You good? Okay, but again, you see this, right? How many carbons are going in? 3. How many are coming out? That's bad. How many hydrogens are going in? 8. How many are coming out? 2. How many oxygens are going in? 2. How many are coming out? We got problems. So guys, this is how we fix the problem. These are, in fact, the chemical formulas for these compounds. But this is what it currently looks like. This is kind of like the Lewis dot structure for C3H8. This is what propane looks like. They used, remember when we did the model kits and white was hydrogen? The problem is white doesn't show up against the background. So gray is carbon, blue in this case is hydrogen, red is oxygen. So guys, we've got C3H8, we've got O2, carbon dioxide, and we got water. You good? Okay, so now we need to start balancing this thing. So this is the way that this goes. I'm going to switch to red. So guys, the thinking goes like this. How many carbons, and you always just start on the left. How many carbons are going in? 3. How many are coming out? 1. So certainly we could just come along and do that, and now we've got 3 carbons coming out, right? No. Why doesn't that work? And the answer is because 3 carbons cannot bond to 2 oxygens. That molecule is no longer carbon dioxide, and it doesn't exist. So guys, if we want 3 carbons, what do we have to do? Well, what we do is we need 3 carbon dioxides. So we represent it like this. We need 3 carbon dioxides. And when we get, check it out, when we get 3 carbon dioxides, so we've got 1, we've got 2, we've got 3. Now that we've got 3 separate carbon dioxide molecules, how many carbons do we now have? 3. Do you see how that makes that balance? So we've got 1, 2, 3 carbons there, 1, 2, 3 carbons there, and our carbons are now balanced. You good? Okay, so now guys, let's keep going. So the next thing we need to then balance are the hydrogens. How many hydrogens do we have here? We've got 8. So to get 8 hydrogens over here, how many water molecules do we need? 4, because 4 packages of 2 is 8. So we put a 4 there, and now I'll do it digitally. So we put 4 there, and now it looks like this. And now we've got 8 hydrogens there, and we've got 2, 4, 6, 8 hydrogens there, and now our hydrogens balance same in as out. So now guys, all we got to do is the oxygens. So how many oxygens do we have going in? Well, we've got 2. Now guys, be careful. How many oxygens are coming out as products? 6 and 4, 10, right? So guys, look, we've got, and I need to switch colors, we've got 1, 2, 3, 4, 5, 6 there, but then we've got 7, 8, 9, and 10 oxygens there. So we have a total of 10 oxygens. So if we've got 10 oxygens coming out, how many O2s do we need to make that balance? We need 5. And so guys, when we get those 5 oxygens, it now looks like this, and now everything that's going in is coming out. You get the idea? Now guys, the challenge becomes this. How are we going to do this when we ain't got the pictures? And guys, actually it's not terribly more difficult, because look, if we just look at what we understand about these, how many carbons are going in? 3. How many carbons are coming out? 3 times 1, that's 3. How many hydrogens are going in? 8. How many are coming out? 4 times 2, that's 8. How many oxygens are going in? 10. How many are coming out? 3 times 2, that's 6. 4 times 1, that's 4. 6 plus 4 is 10. So guys, we can do conceptually what this is doing visually. That's going to be our challenge. So guys, let's try this together. You've already got these in front of you. Do this with me. Grab a... I was going to say grab a pencil, but we've already been through this. All right. So guys, you ready to do this? Start on the left, work to the right with me. So guys, here's how to play the game. How many coppers do we have going in? 1. How many coppers do we have coming out? 1. How many hydrogens do we have going in? 2. How many hydrogens do we have coming out? 2. Now, how many oxygens do we have going in? 1. How many do we have coming out? This is already balanced. Now guys, I know you're thinking, wait, that was weird. Here's why I did that first. Don't do this. Guys, that is wrong for the same reason in algebra class that this looks stupid. You would never write 1x plus 1y equals 1z in algebra class. Why does it look stupid? You don't need the ones. Guys, the same thing is true in chemistry. You don't need the ones. They're understood to be there, so you've got to get comfortable with leaving blank spaces because the blank spaces are understood to be ones. All right, so now guys, moving along. Let's do the next one. How many aluminums do we have going in? 1. How many aluminums do we have coming out? 1. Now, oh wait, and maybe we should say this. Why is it not 3? The 3 only applies to the hydroxide. So guys, with that said, check this out. What is the next thing that we've got? The aluminums are balanced. Well, now we have nitrogen. But here's the thing that's cool. That nitrogen is a part of NO3. Listen to this. It's part of NO3, which is the polyatomic ion nitrate. Guys, go look at your first hint. Look up at your first hint. What does it say? Balance polyatomics intact if you can. So look, guys, we've got the polyatomic NO3. Does it stay intact as a product? Yeah, right there is NO3. So that means we don't have to balance the nitrogens and the oxygens. We can balance the NO3s. So let's do that. How many NO3s do we have on the left? How many NO3s do we have over here? We've got 3 of them. So we've got 3 NO3s on the left. So guys, don't do this. Okay. That changes the formula. NA's +1, nitrates -1. You only need 1 of each. So guys, how do we get 3 NO3s? Put a 3 in front. Now we have 3 NO3s. So now let's keep going. How many NAs do we have on the left? 1. How many NAs do we have on the right now? 3. Because this 3 doesn't just apply to the NO3, it also applies to the Na. So now we have 3 NAs here, which means we need a 3 there in order to have 3 NAs on both sides. Now guys, last step, maybe. We've got O, but O is a part of hydroxide, the polyatomic ion. Do we have to balance the O, or can we balance the OH? We can balance the OH because the OH exists over here as well. But now guys, check this out. How many OHs do we have on the left? 3. 3 times 3, right? How many do we have on the right? Oh my gosh, we're done. And guys, that is not an accident. That is because these things are rearranging by charge, and many times you're going to see things just start magically balancing because nature is cool that way. You okay? All right. And you guys understand this, right? I'm way more purposeful than these just being in any sort of stupid random order, right? Let's keep going. Looking over here, K is potassium. How many Ks do we have on the left? How many do we have on the right? 1. Oh my gosh, look, it's NO3. We've already done NO3. So can we balance the NO3s? Not this time. Why can't we balance NO3s in this example? Because it turns into NO2. We can't balance the NO3s because the NO3 turns into NO2. It doesn't stay intact. So what that means then is we've got to balance the pieces. So guys, how many nitrogens do we have on the left? We've got 1 nitrogen on the left. And then guys, we come over here. How many nitrogens do we have on the right? 1. Notice that the 3 only applies to the oxygen. So we've got 1 nitrogen. So now we need to balance the oxygens. How many oxygens do we have on the left? 3. How many oxygens do we have on the right? Uh-oh. We have an odd number and an even number. We just created an odd-even conflict. You're starting to see that these are in order. So guys, we now created an odd-even conflict. So what do your hints tell you to do to solve that? Double the source of the odd number. So guys, our odd number is right here, so we're going to double that. But now you'll notice that that changed everything. So how many Ks do we now have? 2. So we've got to put a 2 there. How many nitrogens do we now have? Also 2, but we also have 2 over here. Now guys, what about oxygens? How many oxygens do we now have? 6 on the left. What about on the right? Up 4 and 2, also 6. Guys, let's say that again. Sounds like you stumbled on that one. So guys, how many oxygens do we have on the left? 2 times 3 is 6. How many oxygens do we have on the right? Well, here we have 4, 2 times 2. But here we have 2 more. 4 plus 2 is 6. And it balances. You guys okay? All right, so now let's do this one. How many irons do we have on the left? 1. How many do we have on the right? 2. So we need a 2. How many hydrogens do we have on the left? 2. How many do we have on the right? 2. Now guys, SO4. Does the SO4 stay intact? Yep, so we can balance SO4. So how many SO4s are on the right? 3. So we need a 3, and this is now balanced. We already balanced the H2. Oh, so we're realizing that balancing something could screw up something we've already balanced. Oh, so what are we going to do? Well, at the end of all of these, we're going to go back and make sure they're still balanced, because sometimes balancing one thing screws something up we've already dealt with. So now we've got 6 hydrogens, so we need a 3 there. Now guys, here's the thing that you're going to do when you start screwing these up. You're going to get all cocky and you're going to jump straight into the middle of these, and you're going to think, oh, this is easy. I can just plunge in anywhere. I don't need to be metered and orderly and follow a progression. I can just jump in and it'll all work out. Guys, when that doesn't work out for you, start on the left, work to the right, take your time. So let's do one more. Oh, look, it's oxygen. Gosh, I wonder if I should balance the oxygens first. Oh, because we have a rule that says never balance oxygens first because we balance them last? Right. So we're going to go 1 carbon, 2 sulfurs, 1 sulfur. So we need a 2. And then that gives us 2 oxygens on the left for 6 oxygens on the right? Yeah, 6. 2 times 2 is 4, plus 2 is 6. So we need a 3. Okay, so guys, here's where we are now. We have just looked at examples of, and if you look up in your notes, you'll see this. We just looked at examples of the process of balancing equations using coefficients. That's what all of these numbers are. These are the coefficients that we use to balance equations. Now we're going to go up a step. What is the step before that? Write the formulas for the reactants and products. I offer for your consideration this. You'll notice this should be at the bottom of, yeah. It is a description of a chemical process. Calcium metal reacts with copper 1 sulfate to produce calcium sulfate and copper metal. Guys, our challenge is to write and balance the equation that represents the process being described. Here's how you're going to do it. Guys, step number 1 is this. Find the middle of your paper, draw an arrow. Don't fight the process. Take your time, do this, trust the process. Okay, so guys, once you've done this, what we're going to do is we're going to read back through the sentence. And every time we run into a chemical, we're going to ask ourselves 2 questions. What is it and where does it go? So the first thing that we run into is calcium metal. So what is calcium metal? Well, guys, calcium metal is just Ca. So now you're asking yourself, wait, it doesn't say calcium, it says calcium metal. Well, guys, where's calcium on the periodic table? On the left. What does that make it? A metal. You don't need the word, this could just say calcium reacts with. The word metal is unnecessary because calcium is a metal. But calcium is a metal. where does it go? Is it a reactant on the left or a product on the right? How do you know it's a reactant on the left? Because it says reacts. So guys, calcium reacts with. And we represent reacts with the plus sign. So now we've got this. And then we read on, and it says calcium metal reacts with copper 1 sulfate. So guys, our next chemical, if you will, is copper 1 sulfate. Is it a reactant or a product? It's a reactant. It reacts with this. Then we need to know what it is. Well, copper's +1, sulfate's -2. +1 and -2 meet up at 2. So copper 1 sulfate is Cu2SO4. If you can't come up with that, guys, as promised, you're writing chemical formulas for the rest of the year. You got to be able to do this. If you need to spend the time to write down big C, little u, +1 because of the Roman numeral, sulfate is SO4, -2, making whatever you need to do, but you got to write the formulas right. So copper 2 sulfate, copper 1 sulfate. Now it says to produce. Guys, to produce is our arrow. It yields, it makes. That tells us that everything else that's coming is a product. So our first product is calcium sulfate. Calcium is +2, sulfate is -2. We need one of each, and that would be CaSO4. Now notice our other product, aluminum metal. Do we need the word metal? No, aluminum's a metal. Or, sorry, copper metal. Guys, copper is a metal. I don't know where I got aluminum. Copper is a metal. It's just copper. All right, so here we go. So our equation is now calcium plus copper 1 sulfate yields calcium sulfate and copper metal. But guys, you'll notice this isn't balanced. It's not supposed to be. All that we did was wrote the formulas properly, but now that you've got this, this is no different than these. Now all we've got to do is balance it exactly the same way we learned. So guys, we've got 1 calcium, 1 calcium. How many coppers? 2. Over here we've got 1, so we need a 2. Then we've got 1 SO4. Can we balance the SO4s? Yeah. 1 SO4, 1 SO4, and we're done. You okay? Okay. So guys, I'm going to be really upfront and honest with you. This homework assignment is, it'll occupy some time. You're going to want to do this. Well, here, grab your homework packet. Looking at number 1, balance the following reactions. Guys, did you notice the way I spaced them? I gave you space to write in the coefficients. You can balance these right into this. But then, guys, looking at parts 2 and 3, I frankly don't know why we separated parts 2 and 3, because frankly the instructions are exactly the same. It really could just be part 2 and go through J or whatever. Guys, for all of these, you are writing the balanced equations for these reactions just as we did on the board. I was about to say this in a negative sense. I'll say it in a positive sense. You want to do these on another sheet of paper. When you struggle with these, it's going to be partially because you're trying to write these in like super because make these big. Patterns, flow, process. Trust those processes. So guys, these will be due on Thursday. If you are remediating, the first Pride session is today during Pride. If you're ready for that, come and join us. Ready for that means watch the video, took notes, did the homework that's posted. If you are not ready for that, your next and last shot at this is Wednesday, tomorrow during Pride. Understand, guys, that you need to take... Ooh, I forgot. Did you guys pull the remediation letters off your test? If you need the remediation letter off your test, come and let me know before you leave. But guys, tomorrow is the second and last Pride session. Tonight, then, you'll need to watch the video, do the homework. And then, guys, the retest is Thursday. So when I see you Thursday, We will grade this homework, and then we will take the next step and learn to predict the products of reactions. So guys, the rest of the time is yours. I will post the answers on the wall. You've got 20 minutes that you are going to use productively getting these done. You're certainly welcome to work in productive groups, but guys, it's go time. You need to work on these because they're a lot harder than I make them look. So dig in.